This chapter is on the biological effects of nuclear radiation. We've already seen radiation in the previous chapter when we looked at light, because light really is, a type of radiation. And we've seen the electromagnetic spectrum. You do need to know the spectrum, of course. You need to know it in terms of wavelength, frequency, and an energy. So on this end is the high energy, big frequency. Energy, in fact, we know is proportional to frequency, and then also small wavelength. And then it goes in the opposite direction over here. So down here we have low energy, we have a low frequency, and a big wavelength. In fact, some radio waves can have wavelengths that are kilometers or hundreds or even thousands of kilometers long. Remember, this is just a sketch of sort of what the frequency looks like. Our visible spectrum is here. The red is on the lower end, Roy, then green, blue, and then this really violet, which is really just sort of a continuation of blue. They sort of show it as pink there, but it's not pink or purple. Okay, not all radiation is harmful. Visible light is not harmful to the human body. Radio waves are not harmful. They're such low energy they don't affect the human body. But of course, some radiation is harmful. These higher energy gamma rays and X-rays and ultraviolet, they can damage the body. Ionizing radiation, on the other hand, includes nuclear radiation, we'll talk about that nuclear radiation. It comes from alpha and beta particles. And from here on out, I'll use the Greek letter alpha. And beta, I'll use the Greek letter beta particles. We'll describe what these are. And then also gamma rays. Even though the particles are not really radiation, so to speak, we do consider them part of ionizing radiation. And then gamma rays are what we have on the high end of the electromagnetic spectrum. So ionizing radiation includes nuclear radiation and X-rays. So these things, nuclear radiation, alpha, beta, and gamma rays, and X-rays can actually ionize an atom, remove an electron from its orbitals. UV and visible may also be ionizing, but it depends on the atom that they're ionizing. I'll keep going. The nucleus. So the atom consists of protons, electrons, and neutrons. Electrons are negative. Protons are positive. And neutrons, of course, are neutral. They have no charge at all. The planetary model, which was first developed in 1909, this is a model of the atom. In that planetary model, electrons orbit the nucleus like planets around the sun. That's why it's called the planetary model. And this replaced the plum pudding model. Not sure if you know what plum pudding is. I'm not sure that I know what plum pudding is. But in the plum pudding model, there was no distinct positive nucleus. Okay, so in the planetary model, we have a distinct positive nucleus, and then you have these electrons, which are negative, that orbit around it. But in the plum pudding model, an atom was just seen sort of as this amorphous blob, and we had positive and negative particles that were all commingled with one another. Okay, I have a simulation. I'll post a link to this, the Rutherford model, on the website. Continuing on with models, the shell model. In this model, the electrons surround the nucleus in discrete shells. And so as we talk about these models, we're getting progressively more and more correct. That scientists, from the 1900s into the mid 1900s and even to today, that they just sort of come to understanding this quantum world, this very, very small world, much better. And so this shell model came about due to studies in quantum physics. In 1949, the nuclear shell model was developed. And pause there for just a second. Okay, so for these different models, the plum pudding model, the planetary model, the shell model, and the nuclear shell model, just want you to have a basic understanding of them and the progression that they have as we go from this plum pudding, where you have an atom that is just an amorphous thing of positive and negative charges, to where you begin to see a distinction between the nucleus and the electrons, the positive nucleus and the electrons, and then the shell model, where you begin to have these discrete shells. For the nuclear shell model, we're not going to get into this very much, but I just want you to know that the nuclear shell model is kind of like the shell model, except it extends into the nucleus. So you begin to talk about the nucleus also having these kind of shells, but just know that that it was sort of an extension of the shell model that applied to the nucleus. All right, so nucleons is just a term that refers to anything that's in the nucleus, and so it's protons and neutrons in the nucleus. And the number of protons tells the atom, and the number of protons will be the letter Z, the capital letter Z. And it tells the type of atom. Is it a hydrogen? Is it a helium? And Z is the atomic number. The electric charge of the nucleus then is equal to plus Z times the fundamental unit of charge. You remember this E, I'll write it up here, is the fundamental unit of charge. We saw it a couple of chapters ago. And 1E is equal to 1.6 times 10 to the minus 19 coulombs. Atoms typically have the same number of protons as neutrons. We'll see later that's not always true, but typically it is true that they have the same number of protons as neutrons. So if you notice here, for hydrogen, that is the atomic number. Hydrogen has an atomic number of 1. Hydrogen has 1 proton. Sodium has 11 protons. What's this? Rubidium, I think. 37 has 37 protons. So the atom, the number of protons is given by the atomic number, which is on the periodic table. You, by the way, have a periodic table in the back of your book, and you'll need one for the quizzes and exams on this chapter. Atoms that have the same Z, the same number of protons, the same atomic number, but different numbers of neutrons, are called nuclear isotopes. They're variations of the nucleus of a particular atom. They're still the same atom because they have the same number of protons, but if they have a different number of neutrons, then it's called a nuclear isotope, and we'll explore some different isotopes later.